Hello, I'm Hannes. I work for a company called Access, and today I want to talk about the challenges that I encountered while building backend systems. A little bit about me. I am a .NET consultant and a competence coach at a company called Access. This is my Twitter handle and my ICQ number. I'm trying to make ICQ great again. So my agenda for today. First, I want to talk to you all about the hello world of IoT applications. Then I want to talk to you about the real problems that you're going to encounter when you're building IoT applications. And then I'll talk a little bit about shaping data and stuff that you will need to do to your application state when things recycle. And if I have time left, but I don't foresee this, we have some time to talk about maybe actual models. So let's dive right in. Let me first tell you about what your typical IoT stack looks like. Now, if you're building like a huge IoT system, you're gonna need three big parts to it. And the first is all the communication that talks to your devices. So your devices are going to talk to your backend in some way, and you'll need a couple of things to be able to do that. First, your devices will need to authenticate against your backend, and you will need to be able to detect if they're actually online or not, which is what we call presence detection. And then your devices need to be able to send data to your backend and receive control from your backend. So those are like commands and events going in both directions. Now, this is basically a solved problem. You can buy this off the shelf. There's a number of companies that can help you with this. Azure, I listed all the examples from the Azure IoT stack. On Azure, you can use IoT Hub. There's a similar thing on AWS, and there's some third-party vendors you can use as well. So the next thing that you're going to need to do is to process all the data that your devices are sending to your backend. You're going to need to shape that data. You're going to need to enrich it, and you need to go and dump it into some kind of storage, right? And after that, you haven't basically provided any value to your users yet, because all you've done is taken in the data from the device. And this is what we as developers tend to forget, because the fun part is in like processing all the data, but the thing that customers pay for is actually things that they can see in their app and notifications that they're going to get about their devices. So that's the important part. You need to be able to query everything you've processed, and you need to be able to set alerts and to send control, and you need to have dashboards for analytics and all that kind of stuff. So this is the frame of reference that we're going to use today. And I was working for a company that built just this, a backend just like this. And in 2016, I was looking around for better ways of doing this. So I went and looked on the internet, like we all do, and went through a couple of tutorials. And all I could find anywhere was temperature sensor tutorials. And it was temperature sensors everywhere. Now, you might wonder, why is that a problem that we're all talking about temperature sensors? Basically, what happens is you have a temperature sensor and it sends data to your backend. And then you're going to plot that data onto a graph. And basically, when the temperature is too high, you might maybe want to raise an alert. Well, this might be the alert condition. And, well, that's basically all there is to temperature sensors. I'm maybe selling it a little bit short because there is more to it. Because when you're dealing with the heat demand of for instance, your heating system, that connects to a temperature sensor. So it might be a little bit trickier than that, but there is no real complexity to this. Now, if you dive into other types of devices, like these, for instance, these are the ones that are in my house. And you will probably recognize these. They might look different in your country, but these are things that we all know. It's like electricity, water, and gas. And there's a number on those meters. And those numbers are something that we are going to want to work with. And basically what we're going to want to do is to connect an IoT device to that meter, which uses the internet to send data to our backend. And then on top of that backend, we're going to want to provide portals and smartphone applications. Now, if you look at these meter readings, everything that's coming from one of these devices are basically a number. And that number is the reading at a particular moment. But that number is not really what you will care about as the user. Because what you will care about is how much did this number change? Because that's what you're going to get billed for. When your electricity company sends you a bill, you basically get billed for the difference from the number that you are today from the last time that they billed you. So that's basically what we want to look at in our application as well. It's like, how much did the number change? And if you look at this graph, you can see the blue line, which is the meter reading, and it slowly increases from somewhere above 40,000 to somewhere a little bit higher. But that doesn't tell us much. But what is more important is that at 10:15, we used about 20 kilowatt hours. That is important because we can basically link money to that, and that's what we're going to pay. That is what we are interested in. So what do we want to do with this data? Of course, we want to store all of the historic usage. We want to know how much we used today, but also how much we used last week, or maybe the same week last year, so that we can compare these values against other periods in time. Now, we also want users to be able to have some insights into their consumption, so they're going to connect to the backend and actually see their consumption. And what we want to do in an ideal world is when something goes wrong, then we want to basically send alerts to our users. And that is the most important thing, because when our consumption exceeds or undercuts certain thresholds, that is one we are interested in knowing. For instance, if you are measuring the power consumption of a fridge and you see that it stays high for a long period of time, that might mean that you left the door of your fridge open. So that's an interesting situation that you want to send an alert for. Now, what we do with these thresholds, that's not as easy as it first sounds, because this is a very easy situation to see. If our threshold is like, if we have consumption above 90 kilowatts hours over a 5-minute interval, well, it's very easy. We will raise the alert at 10:30. But it's a whole different story if we tell you that we want to raise an alert if we have exceeded the same consumption over a 20-minute time frame. Because if you look at the green and the red lines, it's very clear. It has exceeded the consumption for all of the 5-minute buckets in this time window. So that's a pretty clear alert situation. But if you look at the green line, you see that it dips under it for somewhere in the middle, but on average, it's still above the green line. So what does that mean? Will you need to raise a condition for that or not? And this is basically, it's not a decision that you have to make as a developer. It is basically a situation that you will have to deal with your business, because it's not something that is right or wrong. It's something that you will have to look at. Now, in order to do all this, you might want to shape your data. And also that is a lot harder than it sounds, because when these devices are sending stuff to your backend, you can't count on anything to be correct. A lot of these meters are very, very low powered, have very, very low powered CPUs in it. And they will basically not even give you consistent timestamps, or there is no error correction on the serial bus that you're using to read it. So you might get bogus data for sometimes, or because this happens in the real world, the user's internet connection might go down for a while, and you might miss a whole bunch of those values. And all of that is something you're going to want to deal with in one place, so that for the rest of your business logic, you know that you have consistent data to reason about. What you're going to want to do, for instance, is to correct your timestamps and your buckets. For instance, if we have a meter that sends us data every 1 minute, and we basically have a skew of 25 seconds, like you can see here on the left, we might want to get our timestamps in check and get them exactly on the 5-minute mark every time. Because maybe for the application that we're building, 5-minute buckets is going to be as accurate as we need them to be, and we can basically get away with all the other data. And then we're going to need to interpolate to get the right number for the consumption at a certain time interval. Now it gets trickier. If you look at this graph, the blue dots are the measurement points that we're getting from our meter, but the internet connection only dropped for like 2 or 3 readings. What do we want to do with this? Do we want to fill that? And if we want to fill it, how? Because if we don't fill it, basically we have some orange bars that are missing. And if these orange bars are missing, that means that if we look at our cost for this entire time frame, and it's going to be off. So we're going to need to do something with this usually. But how do you do that? There is no right answer. And maybe if you fill this, you may want to notify all the downstream processes that this data has been gap filled, because it might be very tricky to raise alerts on gap filled data, because raising an alert on a gap filled bucket is always a risky thing because your number might still be off. If you look at this, these are like 6 different ways that I could come up with very quickly how you can basically fill this. And you can basically not fill it at all. And that means that your total sum will be off. Or you can basically put it all into one peak value. You can put it at the beginning of your time frame, or at the middle, or at the end. It doesn't really matter, but it's like one huge peak and it might trigger an alert. So do you want this? And it might seem easy to just split it evenly over the 3 bars that you're supposed to be generating. But if you're basically making them all the same height, you lose all the resolution in your graph. So you could maybe do a trend line, look at the bucket that comes before it and the bucket that comes after it, and then maybe plot a line between those 2 points and use that. Now, it doesn't really matter. All of these are wrong. And the closest you can probably get is look at the same time frame last week and use the same trend line, and then maybe divide your values according to a similar trend line. That's probably the closest you can get. But that takes a lot of processing effort, also takes a lot of development effort. Maybe that's not worth doing. But it's a whole thing that you're going to need to deal with. Now, if you're going down the road and all your downstream processes know that they're getting consistent timestamps and they're getting consistent data, that makes your life a whole lot easier. And you're going to be able to tell, you know that there's not going to be gaps in the data, so all your business logic becomes a whole lot easier to reason about. And I recommend that you deal with this in one place in your application. It makes the whole development process of an IoT backend a lot more straightforward. Now, the trickiest thing about building all this is not normalizing the data, or is not all the stuff that we talked about before. It is recycles of your application. Because to do all this, you're gonna need a whole bunch of state. And whenever you recycle or redeploy your application, all that state from memory is gone. What kind of state do you need? Well, for instance, when you are normalizing your data, you will need the timestamp and the last meter reading that you were using in order to be able to calculate your next bucket. And that's something that you're gonna need to do your gap filling as well. And when you have configured some alerts that trigger after a bunch of time, you're gonna need the last so many normalized values to be able to tell if this alert condition has been triggered. And while your system is running and these meter readings come in, it's really easy to do because you can just keep them in memory and you can trigger the alert when it fires. But what do you do when you deploy a new version? Then all of this is gone. And you might also want to know if the alert has already been triggered and sent to the user, because you don't want to send them a new alert every 5 minutes whenever the whole alert condition keeps existing. So what we don't want is to read all this state from the database every time, because this will severely hurt our performance and our throughput. And let me tell you, we're trying to scale to millions of devices. So we don't want to hit the database for every one of those million devices hitting us with a new meter read. That would just hurt us so bad. So what we also don't want is to only start rebuilding states from events that have happened since we have booted the system, because that will mean that we might have gaps in our data. It might also mean that some alerts might not get triggered correctly. There's a typo on my slide there. Some of them might not get triggered correctly. Some of them might not get triggered at all because you missed the beginning of the alert condition. Or some of them might get triggered again because you already triggered it before you did the recycle, and the alert condition kept existing, and you're getting the same thing after the reboot, and it happens again. So that's stuff that we don't want. Now, let me tell you how we can go about this. Basically, if you look at an IoT hub on Azure, I'm going to assume that none of you are familiar with IoT hub. It's basically an event stream, much like Kafka, and it's basically an event hub underneath. It's an event stream that you have a pointer in. So what you could do is you could have a simple application that just reads from that event stream and that holds a pointer to where it is. And that will just forward all the messages to your backend cluster. You can use whatever you want to do the processing. Now, if we can do it like this, that means that we can basically pause the forwarding of the event, which you will see later is important for us. Then our backend will do all the processing. It will store stuff to various data stores, and we can talk to the backend cluster from all of the business logic that all of the business value that we want to provide. We can read data from our backend. We can basically perform configuration tasks, or we can receive alerts, all of that. Now, when we do our deployment of this whole system, we're basically gonna do it in 5 steps. First, we will pause the process that reads from the event stream. That means that our backend will stop receiving events. And then we can basically wait for all events that were still being processed, that were still in the queue, for that to end. And that's the moment that we know we can safely take it down and redeploy all of our processing cluster. Then we restart it, and the next thing we need to do is to recreate all the state that we were supposed to have in memory. Now, all this state will have to be saved somewhere. So that's something you're gonna need to think about. Is like, how are we going to do this and not lose anything if the system recycles? And then after you have recreated your state, you can basically resume the sending of the messages from the event stream, and everything will continue as if nothing ever happened. And this is the goal. If you do this right, you will not lose any data, you will not get any gaps, you will not get any misfiring alerts or whatever, but it is kind of tricky to do, and it gives you a lot of moving parts to think about. So how can you achieve this in a way that you can still reason about all of the code? And I do have time. I do have 5 minutes, so that's good. I can do that. One of my favorite ways of doing this is using an actor model. And to tell you a little bit more about why I would suggest an actor model, I want you to look at this graph. Now, this graph gives you a whole bunch of statistics about the processor landscape and how it has been for more than 40 years. And there's a couple of trends that you're gonna want to see here. The first thing is that clock frequency has stabilized for over a decade. That's not changing anymore, and it's probably never going to go up again. And what we're also seeing is that our single thread performance is also flattening out. It hasn't quite reached its peak yet, but it's not really increasing that rapidly anymore. There's only one of these colors that is massively increasing over the last decade and a half, and that's the number of logical cores. We went from being mainly single core systems where we needed to upgrade to a faster CPU if we needed to process more data, to CPUs that have so many cores on them. You probably have 8 cores on your phone right now or more. So that's the stuff that we're going to want to deal with, but in able to do that, we're going to need very, very nicely parallelized code. And if you have tried to manage threads in an application and to manage your own thread pool, that is really a really tricky thing to do, because you will run into race conditions, you will have blocking calls, you will probably end up with deadlocks somewhere, and there's always a little bit of your code that you cannot parallelize. There's a little bit of code that needs to be serialized, and this serialization will really hurt your scalability. Because if you look at Amdahl's law, Amdahl's law tells you how much you can increase the speed of a system by throwing more resources at it, given a percentage of the code that can be parallelized. So if you look at the blue line at the bottom, if you can parallelize 50% of your code, it doesn't matter if you throw 65,000 CPUs at it, you're never going to speed it up by twofold. And even 95% will only give you a 20 times speed increase, which means you can handle 20 times the data, even if you throw maybe 4,000 CPUs at it. So 90% or 95% are probably not going to cut it if you need to build a backend that scales massively. And that's basically where an actor model can help you. And I'm a huge fan of Akka.net. This is not a secret. But these actor models can bring you a couple of advantages that help you build these kind of systems. First, they bring you the high degree of parallelization that we want to have. And especially for stateful system, because as we established a little bit before, we're going to need to have a lot of state in memory if we're going to be normalizing data. If we're going to calculate alerts and different conditions, we need a lot of state in memory, and that's what an actor model can help you with. It's built on reactive patterns, and the cool thing about this is that any little bit of business logic is really easy to reason about, because there's a very, very easy way to tell what in and outputs there are, because all these actors, they receive messages and they send messages. So you can reason about what one actor does in a very, very contained way. And that makes the maintainability of your code a lot easier. And there's also a cool thing, but that we're not going to dive too much into today, but actors allow you to build a very fault-tolerant system, something that can self-heal if something goes wrong. Let me quickly tell you what an actor looks like. An actor is like a simple class. There's actor frameworks on a lot of different programming languages, so this probably holds true for most of them. An actor is a very simple class, and it has a method to process messages. And these messages are held in an inbox. And it just processes them first in, first out, one at a time. And this is very cool, because that means that your actor will only have one single thread running on it at the same time, which means that you don't have to worry about locking resources. You don't have to worry about synchronizing threads, because everything that's running on your actor at that moment, that's only going to be one thread. And all the behavior are just functions in your actor, and all the states are just fields in your actor, just like any regular C# or Java class that you're used to writing. So this makes reasoning about the code a lot easier, but what you're going to need is to some kind of orchestration system that basically manages all these actors. And that is your actor system. Your actor system will manage all the life cycles of the actors. It is responsible for spawning them. It is responsible for recycling them. It is responsible for dispatching messages to every single actor. It will manage the inboxes and so on. And most importantly, it will handle all the scheduling of the threads, which is the thing that we don't want to do, because it is very, very tricky and we want to stay away from that. So that is what the actor system, much like a puppet master, will do for us. This is still by far the best metallic SCD that there ever has been. Fight me on that. Now, good. How do these actors look? You have an actor hierarchy, and the place where your actor lives in the hierarchy determines its address. There are 3 actors that you cannot control. This is basically Akka.net related. You will have a root actor, a user, and a system actor, and then you can spawn your own. And the ones that you spawn directly under the user actor are your top level ones, and everything below that are just child actors. And basically every actor can spawn as many children as they want. Now the tricky thing with children is, if you have children yourself, I have 3, so I know, if you have children, you are responsible for them. If you take your kids to the supermarket and they misbehave, you are still, as a parent, responsible for what your children do, which means you will have to take corrective action when things happen. If they break something, you're going to have to pay for it. If they offend a stranger, you will have to apologize, all that sort of stuff. And basically with actors, it's the same thing. If an actor fails for some reason and it throws an exception, it will basically get escalated to its parent, And that parent will have to choose what the action that has to be taken will be. You can either say, okay, this exception is not that bad, we're just going to resume, continue as you were. You can decide to completely restart that actor. That means that the state gets lost and it is respawned, but the inbox is preserved. Or you can decide to like stop it altogether. It's like, okay, if you failed doing this, there's no point in continuing execution, and you just kill the actor. And you can decide to do this depending on your workload for just the one actor that failed or for all your children. Why would you want to do it for all of them? Basically, if you have a huge workload that you split up amongst a lot of child actors and a single failure invalidates the whole workload, then you want to kill off all the processing on all of your children. Now this, if you apply this to our, all this actor system stuff to our IoT system, which it means that, for instance, the B level of actors that you see here, they might have one actor there for every single device that we're talking to, which means that we can keep the state for that single device in that actor, which means that it's very easy to take in a new measurement and basically deal with that in a very, very confined way. And it doesn't really matter. It will not get in the way of all of the threats of all the other device actors that are in our system. Now, if we go back to this picture that I showed you earlier, what part can you basically use an actor model for? Basically, it's a good solution for anything that is basically shaping the data, processing the data, doing alerting on it. It's not really meant for storage. You can use it for storage. You can basically have Akka.NET persist some of its state, and it's very useful if you look at my full talk about this, drinking a river of IoT data with Akka.NET. You will basically see how you can apply Akka.NET storage to help your system be more resilient and to deal with the restoring of state when the system recycles. The actor model can help you with that. It's not really meant for building dashboards, so basically you're gonna build all your apps on top of the cluster and they will just talk to it.